welcome you to this lecture on marine hydrodynamics. In the last lecture, we are talking about water particle kinematics of the water particles, and we have seen that the water particles they follow an elliptic path, and in case of infinite depth, the path becomes circular in nature. And again we have seen that how the resonance occurs in case of a closed and open basin, and we have seen that in case of wave oscillation in a tank or in a bay or the bay or basin, it is the primary modes of oscillation which plays significant roles. Today, earlier also I had mentioned that out of there are several types of waves that exist in the ocean, and one such a wave is the capillary gravity waves, and that is due to it is basically the effect of surface tension on gravity waves. So, and that is why we call it, because capillarity comes from the capillarity and gravity waves. So, basically it is the effect of surface tension on gravity waves. So, let us see how this equation comes into picture, or how the boundary condition on the surface is changed or the wave motion is affected in the presence of surface tension. We all know that the pressure P 2 minus P 1 is equal to T into 1 by R 1 plus 1 by R 2, where if basically if I have y is equal to eta is the free surface, if this is the free surface, and so 1 by R 1 plus 1 by R 2 basically the mean curvature, of the curve y is equal to eta. Then we have seen P 2 minus P 1 is the difference of pressure, or we call it as the gradient of pressure, and there is a difference of pressure on both sides in the presence of, so that varies as the mean curvature, and we have seen that grad P is equal to T into 1 by R 1 plus 1 by R 2. Now, what happened in case of a free surface? In case of a free surface, my P 1 is the hydrodynamic pressure, and my P 2 is the pressure at the atmosphere pressure. In fact, we have seen when P 1 is equal to P 2, we used to say that hydrodynamic pressure is the case as the atmospheric pressure. On the other hand, if there is they are not same, then what we say in case of capillary rise, this grad P varies as 1 by R 1 plus 1 by R 2, and this is called where T is the surface tension force. Then it is and T what we call the coefficient of surface tension or the surface tension itself. So, then what happened here, P 1 is the hydrodynamic pressure. So, P 1 in the P 1 by rho is equal to G eta plus del phi by del T, and again but what will happen to P 2? My P 2, then P 1 from this equation P 2 minus P 1, that is P 2 minus P 1 is equal to T times 1 by R 1 plus 1 by R 2, and 1 by R 1 plus 1 by R 2 is nothing but T times del square eta by 1 plus del eta by del x. This is the definition of curvature. By 2, and that gives me, because if I assume the surface eta is small, then on the free surface this will be T del square eta by del x square, del square eta by del x square, because I assume eta is small. So, del eta by del x will be again smaller, its square will be very small. So, this term will give him 1, and then this becomes, so P 2 minus P 1. So, which implies my P 2 to P 1 plus so P 2 is a P 1 so my P 2 minus P 1 is sorry, there is a P 1 is the hydrodynamic pressure and P 2 is the, so this should be, sorry, there is a, this is, sorry, P 1 minus P 2. So, this is P 1 minus P 2. So, my P 2 is the atmospheric pressure. So, P 2 will be P 1 minus, sorry, minus T into del square eta by del x square. So, this is my pressure, and this pressure is nothing but my P 2 is the atmospheric pressure. So, this will be 0. So, if P 2 is 0, P 2 is constant, P atmosphere, and that I assume as a constant. So, on the surface we have P is equal to P atmosphere. So, in the process what happens? So, I will have, that means my P 1 minus T del square eta by del x square is equal to 0, and on y is equal to, I can call this eta. Again what happen, if I substitute for P 1 is the hydrodynamic pressure, P 1 is rho by rho into phi T plus g eta, and that is minus T del square eta by del x square 0 on y is equal to eta, and that again for the, because I am considering the linearized water wave theory. So, this y is equal to eta can also be reiterated as on y is equal to 0, because higher order terms will not contribute, and in the, again in the, in this derivation of P 1 I have only taken the linear part. Now, linear parts I have neglected, because I assume that eta is small, as we have done it previously. So, then in that process what will happen, it will give me rho or phi t plus g eta minus T by rho del square eta by del x square 0. This becomes on y is equal to 0. This is the linearized, it becomes the linearized dynamic condition on the surface in the presence of surface tension. And we all know that the kinematic condition, this becomes, the kinematic condition remains the same, phi t is equal to g eta on y is equal to 0. This becomes my kinematic condition, and this is the kinematic condition, this is my dynamic condition. Dynamic condition in the presence of surface tension, this is, if I combine these two, that gives me phi t t plus g eta t f phi t plus g eta, or phi t, sorry, it will give me eta t is phi y, sorry, phi y, sorry, this is not this, it is gives me phi y is eta t, this is on y is equal to 0. This is my kinematic condition. That comes from d by dt, y minus eta is 0 and y is equal to eta. So, this is what So, so if I combine this, eliminate eta from the dynamic condition, this is the kinematic condition, that will give me phi t t plus g eta t will give me phi by and minus t by rho. Again I have eta t, that will give me phi by, so that will del q phi by del x square del y is equal to 0 and y is equal to 0, which can also be using Laplace equation, that I can also call phi t t plus g phi y plus t by rho phi triple y, all this is a capital Y is 0 and y is equal to 0. In fact, this is the linearized free surface condition in the presence of surface tension, and this condition is very important, because if we have seen that if t is equal to 0, that means if there is no surface tension, then what will happen, this term will contribute 0. So, we have phi t t plus g phi y is 0, and that becomes the free surface linearized free surface boundary condition in case of gravity waves, and in case of capillary gravity waves this extra term is coming, and here we see that there is a third order term in the derivative itself that is contributing coming into picture. Now, if I just take this free surface boundary condition, suppose I say that I have a wave eta is equal to a cos k x minus omega t, and as I have seen, we have seen that in that case there will be a phi which will of this form, and if you substitute for this phi, where phi satisfies the Laplace equation, this will satisfy the Laplace equation if it also satisfies the bottom boundary condition. On the bottom boundary you have phi y is 0, this is y is equal to minus h, and here y is equal to 0, on the y is equal to 0 you have the condition is phi t t plus g phi y plus t by rho phi triple y is equal to 0, and you have here del square phi is 0 in the fluid domain. This is the main free surface, this is the bottom surface, the linearized case, and in that case what will happen here, we can easily see that if phi has to satisfy this equation, you will see that this will give us phi t t will give us omega square, this will be cos hyperbolic h, and that will be minus will be there. So, if I bring this g phi by g k plus t by rho k q to sin hyperbolic k h, which is same as omega square by g is equal to k plus k into 1 plus m k square tan hyperbolic h, which can be written as, and here, so if I call this capital K, it is equal to small k into 1 plus m k square tan hyperbolic k h, and here capital K is omega square by g and my m is t by rho g. So, under this, notice under this, if you use this symbol, then k is this, and this equation, this is the dispersion relation for the capillary gravity wave. That is dispersion relation for capillary gravity waves. So, here this exists because as I have seen that when there it is only exists when there is a change in the two sides pressures are not same, there are the P 1 minus P 2, as we have seen from the definition that varies as the mean curvature. That means, in this case of surface tension, the two surfaces there is a difference in the pressure on both sides, and in the process we got a capillary rise because the surface the rise means the pressure on the higher is higher on the atmospheric pressure is higher than the pressure hydrodynamic pressure in this case, and because of that there is a rise in the fluid, and that rise. So, that is why there is a capillary rise, and we have seen that in that case we have the dispersion relation is this. Again, if you analyze this, what will happen when K h is becoming much greater than 1? In that case, it will give us capital K equal to small k into 1 plus m k square, and this gives us a cubic equation in small k. If we assume that we know capital K and we know m, then it is a cubic in small k, and it will have two roots. It can be seen that k 0 and this will be alpha plus minus I beta. It can be easily checked that if k there is it has one real root, this is real, and there are two complex roots. Further, if I look at this equation further again, that if k h is much less than 1, that means in case of shallow water we will have k into 1 plus m k square into k h is equal to capital K. So, that gives us that k into k square h into 1 plus m k square is equal to k. And there will be 4 roots. Out of that, it can be easily seen that plus minus k naught are the 2 roots, real roots, and it will have further again 2 complex roots, 2 real roots and 2 complex roots. So, in this case it has 4 roots, and on the other hand, in case of the general case, k into 1 plus m k square into tan hyperbolic k h is equal to k. If you look at this one, and this dispersion relation has one real root k 0, alpha plus minus I beta are the 2 complex roots, and plus minus I or I p n are the infinitely many imaginary roots. So, this give these are all the roots of the dispersion relation associated with this equation. So, I will come after some more roots after some time that how these roots are, what is the behavior of these roots and how they depend, what is the maximum minimum, how this behavior, how the root behavior will analyze a little later, maybe the next lecture, but today I will rather spend a little time to before going to the root behavior. I have to talk a little about something about the group velocity and the phase velocity of gravity-waves and then capillary gravity-waves, and after that I will come to this. So, let us and then again another thing, once we know eta, we can always phi, because we know if you applying the kinematic condition, because we have already know for the eta is equal to a cos k x minus omega t, we have the corresponding phi is equal to a cos hyperbolic k into h plus y into sin k x minus omega t, and using the kinematic condition or the dynamic condition, we can easily get a relation between small a and capital A, and I leave this as an exercise. Relate a with a. This is very simple as I have done, but I am not going here, but I leave this as an exercise. That is a simple exercise which can be derived easily. Now, with this understanding, let us I will come to in detail about the behavior of these waves, particularly how the capillary rise affect the wave motion, that I will come a little later. Before that, let me talk about the wave energy, basically the group velocity or wave envelope. we have seen that c is equal to lambda by t, and that gives us the rate at which the wave travels, a monochromatic wave of frequency omega or the time period t it travels. And this we have also seen that if we have two waves and another wave eta 2 is cos k x plus omega t, we have seen the resultant wave is eta is equal to eta 1 plus eta 2, that gives us a standing wave, and that standing wave has amplitude twice that of the individual progressive wave. This is plus. And so, what we have seen that here amplitude of this wave, this generates a standing wave and the amplitude is twice that of the individual that of the individual waves, and here both the waves have the same amplitude, only problem is that they are opposite in direction. The two wave propagate and they are opposite in direction. Again we have seen that when there is a change in amplitude, when we have two waves of different amplitude a 1 and a 2, then we have seen that it forms partial standing wave or partial Clapeyron. But here the waves are propagating in the opposite direction, but amplitude only variation in the amplitude, and here in there is a amplitude variation and also variation in direction. My question, second question comes, what will happen if k 1 is not equal to k 2 and omega 1 is not equal to omega 2? What happen in reality when there are in ocean waves? We have always seen that waves of similar nature propagate, but always it need not be the same wave which propagate. So, when k 1, that means I am looking for waves when k 1 is behaves like k 2, omega 1 is behaves like omega 2, but the amplitudes of the waves are same, whereas they are similar in nature as far as the wavelength of the waves and the period of the waves are concerned. In such situation, how the, suppose I have two such waves, eta 1 is equal to a cos k 1 x minus omega 1 t and eta 2 is a cos k 2 x minus omega 2 t. But I say they are similar in nature, but they are not exactly the same. In this situation, what will happen to the resultant? Eta is equal to eta 1 plus eta 2, and that gives me 2a. This will give you cos k 1 minus k 2 by 2 into x minus into we have cos k 1 plus k 2 by 2 into x minus omega 1 plus. So, this is the resultant wave. Now, what will happen if I look at this resultant wave? There are two things I will observe. There are two, in fact, it is a looks like a standing waves, and these standing waves has so my resultant wave is basically 2a cos k 1 plus k 2 by 2 into x minus omega 1 plus omega 2 by 2 into t multiplication by ks k 1 minus k 2 by 2 into x minus . Okay. So, now what will happen, because this is, there are two things here, this is again a wave, this is again a wave, super is a product of two waves. So, what will happen when k 1 approaches k 2 and omega 1 approaches omega 2? If these two are same, then this part, the first part becomes the same as the one of these initial waves, original waves, but what will happen the second part of the waves. So, this way this becomes, if I look at this one, in that case this becomes twice that of the individual waves, but what will happen to this part? and that will be more obvious because they are not going to be, this part is not going to happen the same way. So, what will happen in this case? If I look at the, let us analyze it from the point of view of the phase velocity. The first case, the phase velocity c will be because omega 1 plus omega 2 by k 1 plus k 2, and if I say k 1 omega 1 is turning to omega 2, then this will be give me omega by k. That comes from the first part. But what will happen in the, if I look at the second part as my wave, and this part I take as the envelope amplitude of the wave, then the second part my C g, I will call this as a C g, and that it gives me omega 1 minus omega 2 by k 1 minus k 2, and this is when k 1 tends to k 2 and omega 1 tends to omega 2. So, this is if I just say limit k 1 tends to k 2 and omega 1 tends to omega 2, that will give you del omega by del k. I call it limit del k tends to 0, and that gives me d omega by dk, and this I call it as C g. So, my C g is nothing but d omega by dk, and what is d omega by dk? D omega is the frequency of the waves. So, d omega by dk tells me the rate at which the waves of similar nature they propagate. That means that gives in the rate at which the wave energy propagate. In fact, it can be easily seen that this will give us, and this I call this as the group velocity. So, if I look at this, how they will look like, the wave will actually look like this. This is my actually the wave will propagate like this. This is the way the wave will propagate, and this is the envelope. So, the combined wave will propagate in this pattern, and this will follow this. So, to an observer it will look like as if an a wave envelope, often we call this as a wave envelope, and it is the rate at which the. So, the total wave it looks like the wave envelope, it is a group wave group. In fact, in the ocean when we see the wave that we see, that always it looks like, it always the wave envelope or wave group which propagates, it is not the individual waves what we see, and this is the wave, and then in that case this is the velocity is d c g, that is d omega by dk. So, now if you look at this, let us look at this d omega by dk. What happened? We all know that omega square is g k tan hyperbolic k h. Then what will happen to d omega by dk? So, d omega by dk will be 2 omega, and then this will give me d omega by dk, that will give me g tan hyperbolic k h plus g k h sec hyperbolic square k h, and that gives me one by 2 omega. This will give me g So, if I take and this will give me, I will call it by 2, let me call it sin hyperbolic cos hyperbolic, call it sin hyperbolic 2 k h 2 times 4, or 2 is gone to 4 plus 2 k h divided by cos hyperbolic x square kh. And if I take this, I will write it g by 4 omega square, which I call it sin hyperbolic 2 kh by cos hyperbolic square kh. I can call it 1 plus 2 kh by sin hyperbolic 2 kh, and this I can always write this sin hyperbolic 2 kh will give me, this will go, this is sin, 1 cos will go, so this will give me 2 g by 2 omega, and this will give me sin tan hyperbolic h. And tan hyperbolic h 1 plus 2 kh by sin hyperbolic 2 kh, and tan hyperbolic 2 kh will be omega square by g, g by 2 omega into omega square by g, gk, and then that becomes 1 plus 2 kh by, so I have omega, this omega will get cancelled with omega, g get cancelled, that will give me c by 2 into 1 plus 2 kh. So this is what, this is my Cg, and that is nothing but d omega by dk. So what I am getting, my Cg is c by 2. So the group velocity Cg is nothing but c by 2, c is the phase velocity, into 1 plus 2 kh by sin hyperbolic 2 kh. This is the most general expression, and this is the rate at which the wave energy propagates. And then we can see that easily that when kh is small, when kh is small, we have 2 kh sin hyperbolic 2 kh, and that case Cg is c. On the other hand, when kh is large, then we have Cg will be c by 2. So in case of deep water, you can always say that the phase velocity, the wave energy propagates at a rate which is half of the rate at which the individual monochromatic waves propagate. On the other hand, in case of this is in case of shallow water, in case of shallow water, you can say that the energy propagation is same of the individual wave propagation. The speed of propagation of the individual wave is the same as the rate at which the wave energy propagates. Now this is another interesting result which we can use at a later stage and see what happens. Now another thing here we will see that in case of standing waves, I will come to the capillary gravity waves later, but let me analyze a little more about the standing waves. We have seen that in case of a standing wave, eta is equal to 2a cos k x cos omega t, and if it is 2a cos k x, then the corresponding phi will be, we have seen that it is minus 2a omega cos hyperbolic k into h plus phi to omega cos hyperbolic by sin hyperbolic k h into cos k x into sin omega t, and from here let us look at what happened to phi x. Phi x is minus 2, this will be plus 2a omega k Similarly, what will happen to phi y, and phi x is nothing but u, phi y is nothing but v, and phi y will be minus 2 a omega, again k, this will give me sin hyperbolic k into h plus y by sin omega t. And we have seen that on a wall, if it is a phi x is a wall 0 on a wall located at x is equal to a, then we have seen that a will be n lambda by 2. And we have seen that because these turning waves and near the wall, we have also seen that near the wall antinode will be formed. But then in that case, what will happen to phi y? Because phi x is 0 near the wall, what will happen to phi y at the same point? Phi y will be, because phi x is becoming 0, but phi y, what will happen to phi y at x is equal to a is equal to n lambda by 2, and this we can say that phi y will be at the maximum, that will 2 a omega k, because it will be cos n lambda by 2 k into n lambda by 2, and that will be plus minus 1. So, if I look at the maximum velocity, that will be v, I take the maximum of this, that will give me 2 a omega k sin hyperbolic k into h plus y, because into this part will be plus minus 1. So, this is I have taken the positive sign. So, this will be into sin omega t. This is what. So, that what will tell, so that the vertical velocity at that point v becomes the maximum, this becomes maximum. So, although antinode form, although in a standing wave near the wall, antinode is formed. So, and here horizontal u velocity value u is 0, but at the same time v becomes maximum, v is v max. So, that is what happen here. Another point I want to look into, in both the cases u and v, if you look at the sign part, time dependent part, both are sin omega t terms, because this is not affected. Now, what will happen if sin omega t is 0? If sin omega t is 0, which implies both u and v are 0, and once u and v are 0, we will see later that u and v from the energy definition, kinetic energy definition, that will show that will lead to kinetic energy at 0, because u is 0, and once the kinetic energy will be 0, because the energy will be constant. So, in that case what will happen? The potential energy will be maximum, and when sin omega t is becoming 0, u v becoming 0, and the kinetic energy is becoming 0. On the other hand, what will happen? The potential, on the other hand, what will happen? If I just say that instead of sin omega t 0, if I just say that my eta, because eta has a term 2 a cos k x cos omega t. So, in this case, suppose what will happen if cos omega t is 0? If cos omega t is 0, then once cos omega t is 0, that means eta is 0. once eta is 0, then what will happen? The potential energy will be 0, because it can be, we will see that we will come to the definition of kinetic and potential energy, but once the surface is not moving at all. So, the potential energy will be 0, and once the potential energy is 0, because the total energy is the combination of the kinetic and potential energy. Once the potential energy is 0, the total kinetic energy will attain the maximum. So, here this also not only the both the behavior of not only the space component is contributing, spatial derivative, spatial component is contributing, the time component is also contributing to the wave motion, particularly the transfer. So, what is happening when the particularly this sin to cos, if eta changes sin to cos at the interval of pi by 2, there is a phase change. If once there is a change of phase of pi by 2, then the, so that what happens? If you look at the standing wave pattern, so this is total is 2 pi 0 to 2 pi. So, at a very basic interval of pi by 2, so this is 0, this is pi by 2, this is pi, this is 3 pi by 2. So, we see that at every interval pi by 2, eta is changing from, if eta starts from here, then at the interval of pi by 2 from it will reach here, and here if this is the total energy, the eta is 0 here at this point, and that means potential energy is 0 here, the kinetic, and here the total energy is always in this way. And then on the other hand, when it comes here, the wave energy propagates, maximum energy excitation is in this way, again it reaches here, the energy excitation becomes in this way, and again when it reaches here, whole energy excitation is in the vertical way. So, this is the way how the energy. So, it is always that the energy transfer from kinetic to potential and potential to kinetic takes place alternately, and this form. So, there is a periodic changes from of transfer of energy from kinetic to potential and potential to kinetic, and it takes place in an alternate manner, and it also in a periodic manner. So, this is what. Now, with this I will go to the basic definition. Now, let us see what happened about the energy associated with the wave. If I look at the energy associated with the wave, in fact, I will just define what exactly the how the energy transfer is taking place. If I look at the, let me define the potential energy and kinetic energy. How we define the potential energy? So, the potential energy per is the energy, rather potential energy per, I will talk it as energy density per unit wavelength, and over per unit wavelength and unit time, and that will give me that 0 to L, and that is this is rho j by 2 T L 2 T lambda 0 to lambda, then it is eta square, that is dx dt, is a double integral 0 to t, and this if you calculate it, take eta is equal to A cos k x minus omega t. If you one calculate the total energy, it will give me rho g square by 4. In a similar manner, what will happen to the kinetic energy? That will be, because by the basic definition kinetic energy will be rho by 2 half, it is like half mv square into 0 to L, 0 to the mean free surface is minus h to eta, because it is the free surface is variation from y is equal to minus h, this is y is equal to eta. So, minus h to eta, then we have over the total interval as 0 to t, and that is phi x square plus phi y square dx dy dt, and that will be by t by lambda. And if you calculate this, you will also get, I am not going to rho g square by 4 again, and that will give me the total energy E as E k, energy density rather I call it E k plus E p, that is rho g square by 2, and A is h by 2. So, I can call it rho g into h square by 8. So, that is the definition of energy, E is rho g h square by 8. So, this definition is rho g h square by 8, and that says that as if the wave energy rho E varies as h square. Here I am not going to the detailed derivation of the energy, but this once we know eta, we can easily find what is phi and what is phi x, phi y, and substitute for this in the definition of energy, and we will get it. It is quite simple, and we have seen that. So, in fact, many situation E varies as h square, or we can call it E varies as amplitude square, A is h by 2. So, and these relations are very, in fact, it is because of this in the data collection, ocean data wave data collection, particularly waveguide data collection or data collection of wave amplitudes by satellite, many times the energy spectrum is collected. Energy spectrum, many times we get the energy spectrum. That means, because once we know the energy spectrum, or in that case, that means we get the energy and we get the a square. That means, we know that E varies as a square. So, once we get the energy from energy, that means we know h square, and once we know h square, then we can easily get h. So, in many situations in satellite data collection or other form of data collection, many times we get the energy associated with the waves, energy spectrum what we say, particularly how the wave data we collect it, that is this is omega, and that is E square or E or A square omega, or in case of amplitude spectrum we always get it omega and we call it A omega. These are all continuous spectrum, but in case of a discrete spectrum, what we do, we have been given data, various data are there, discrete data. So, this is maybe A n, A omega n, this is omega n, and this is, or we get it A square omega n, that is omega n. So, we get it various types of data, and these are discrete spectrum, these are discrete spectrum, these are all continuous spectrum. This is amplitude spectrum, we call this sometimes amplitude spectrum, or this is called the energy spectrum. So, this is very important in case of ocean data collection, and that, and of course, I am not going to the statistical distribution or the probabilistic distribution data here, but but here one has to make a note that when the amplitude spectrum is collected, it is basically the wave amplitudes are known, but in case of energy spectrum data is data distribution in terms of energy spectra, then we say as if the amplitude square is known. So, this is what is and that comes because always we know that it is the energy is always varies as the amplitude square or the wave height square. So, that is another point to be noted. Now, with this understanding, so I will just make another point. What is energy flux? In fact, conservation of energy. It says that the total energy, the conservation of energy says the grad of ECG is constant, ECG is 0. That means, the total energy, that is through any cross section you think of, the total energy passing through it any space, there is not much, there will not be, it is always, if I put it in a integral form. So, it will give me ECG is constant. That means, you look at any cross section, when the wave energy propagates through any cross section, the energy that propagates through any cross section is the same. So, that means, and what is E? E is rho g h square by 2, h square by 8, whereas C g, we have already C g is the group velocity, and that is nothing but c by 2 1 plus 2 k h by sin hyperbolic 2 k h, and that is, this gives us the group velocity. This is the wave energy associated with a single wave, whereas this is the energy flux, conservation of energy flux. In fact, when the wave propagate over a surface or when the ocean wave propagate, every time it follows this energy flux, because this equation is constant. And I will just say in brief what happened. Suppose C g is equal to C, and that too in case of shallow water. So, that is root g h. So, in shallow water, in case of shallow water, and then what will happen? E is rho g h square by 2, 8 into, if I say in case of shallow water, I put it g h. So, that gives me constant. So, which gives me h square root h is equal to constant in case of shallow water. That means, my if I have a initial by h 1 by h 2, this will give me h 2 by h 1 to the power 1 by 4. This is what happened in case of a shallow water. So, when wave propagate from a deep water to shallow water, deep water region to shallow water region, so there is a change in the amplitude, because as we say, when the wave propagate from deep water to shallow water region, the amplitude changes, amplitude goes on increasing, and that follows this, and this is often called, this as known as the Green's law. So, there is a change in the amplitude, particularly the wave height, the depth. Once there is a change in the water depth, if there is no refraction, and this process of change in the water depth associated with the change in wave height is referred to as swirling. And in case of shallow water, this follows this. If there is no refraction or diffraction, only the water directly to propagate to the from the deep water to shallow water. Suppose there is change in water depth, then they will follow this rule, and that comes from the energy, wave energy, conservation of the wave energy flux. And this is particularly, this relation is in case of a shallow water, but in general this is this. So, that is another observation which is very important one has to. It is very easy to, although it is very easy to show that the, but it is gives us a clear idea about that how the changes takes place when there is a change in the wave height and how the water depth is related. So, with this today we will conclude the lecture today, and tomorrow we will go into other details about the wave characteristics, particularly a simpler few more cases will consider about the how the conservation of energy flux is used in various other cases, particularly in case of a deep water or in case of water of intermediate depth through an example, and that will come in the next lecture in detail. Thank you all.